I am Orsolya Gáspár. I am an architect and an assistant professor at BME Budapest, and my talk is about Bauersfeld's concept for the subdivision of the first built geodesic dome structure. The Miracle of Jena is the first temporary planetarium dome designed by Walther Bauersfeld, the man to the right, chief engineer of Zeiss, a major producer of optical instruments. The dome was built to test his invention, the projecting device for the planetarium. Our interest is its steel reinforcement covered here with a light layer of sprayed concrete. That was the first built geodesic dome structure seen on the right here during erection. It was built in 1923, more than 25 years prior to when the term geodesic dome was first used by Buckminster Fuller on the left. One of Fuller's earliest concepts was the so-called alternate subdivision based on the spherical icosahedron. The Jena dome is also based on the spherical icosahedron, and its subdivision, highlighted in bold black, is the class 1 type, just as the alternates. I will shortly explain these terms better. Anyway, it was long believed that the original documentation of the Jena dome was lost, so based on visual comparison, it was assumed in the literature that the subdivision of the Jena dome was equal to Fuller's. The problem statement of this talk originates with an open question suggested by Professor Tibor Tarnay during the IASS symposium held in Hamburg back in 2017. He argued that based on the ingenious concept for the projecting device which he studied, he believed Bauersfeld was not someone who would settle for the alternate subdivision, which is though simple in its construction, but far from being optimal. Almost all rods in such a subdivision have different lengths, and they deviate quite much from each other. He pointed out that there are numerous other class 1 type subdivisions of the spherical icosahedron and suggested the problem needs further investigation. I heard his speech, approached him afterwards, and here we are. Before we proceed, clarification of the terminology is necessary. The geodesic dome's grid is the result of the subdivision of the faces of a regular, such as the icosahedron which Bauersfeld used, or semi-regular polyhedron projected onto the spherical surface. Class 1 type triangulation of the spherical polyhedron roughly means that if its face was projected onto a plane, the small triangles would be similar to the big one. The frequency of the subdivision equals the number of triangles along the edge of the unit face. Hence, to the right you see a 4-frequency class 1 type subdivision, while Bauersfeld type is a 16-frequency as shown on the left. Bauersfeld was believed to optimize his design. But what makes a good geodesic dome? From an aesthetical point of view, they need to be smooth. This translates to being subdivided to equilateral triangles or as close as possible. From a practical point of view, it would be great if they had the smallest possible number of different edges also, as it would simplify post-production and assembly. What did Bauersfeld think about optimization? One of the key findings of this study was that he actually thought about it a lot. He listed his preferences in his manuscripts kept at the Zeiss archive explicitly. He wanted the project onto the dome surface, so it needed to be smooth. He introduced the benchmarking parameter edge-length ratio to measure this, which later became, independently from his work, standard. He also wanted the brace dome to approximate the behavior the best it could, that of a membrane shell, in order to be able to assess its structural performance. He believed from early on that an equal area triangulation of the sphere would be most suitable to meet his aims, and tried various ways to achieve this. The equal area tessellation of a geodesic dome is a very interesting idea theoretically, as to my knowledge no similar attempt has been taken ever since. At the end of his notebooks I found this: a detailed drawing of the subdivision of the 1/6 of the face of the icosahedron and the accompanying calculations without further explanation. After figuring out the equations, it became clear that the described algorithm results in an almost equal area subdivision. I refer the listener to the paper on why it does not and cannot result equal areas. What this algorithm does is that it first divides the spherical triangle ABC by the edge CD into 1 to 3 areas, then successively halves the bigger part highlighted until reaching, in step 5, the area E6. The remaining bigger triangles are also accordingly subdivided, leading to an 8-frequency subdivision. Then at the last step, Bauersfeld simply halved the edges of each spherical triangle to reach the desired 16 frequency, which I promised earlier in this talk. No argument is provided as to why he chose to alter the algorithm. A comparison to other subdivision methods might provide an explanation though, while also highlighting how well-performing the Bauersfeld type is. Both the number of different edges and the edge length ratio are the smaller the better. The first row contains the data of the Bauersfeld type, as I explained before. The second row is a hypothetical one. If the 16th frequency was reached with halving the areas all the way, note that it would have resulted more different edges, and these are compared to the method of side-bisection and Fuller's alternate. It's obvious that the Bauersfeld type exceeds the rest in almost all parameters, but the side-bisection comes close. So far so good. The only problem is that there is no explicit proof that Bauersfeld indeed applied the subdivision method that I just described. We know he played with the idea of equal area tessellation from the start, but still, it was safer to check. So I built the 3D model of Fuller's alternate, the side-bisection, because there were traces in his manuscript suggesting he contemplated that idea as well, and of course the Bauersfeld type subdivision, and compared it to the original photograph of the dome during erection. As this comparison shows, the Bauersfeld type matches best, while the Fuller type worst. Now I can state with reasonable certainty that the Bauersfeld type subdivision was applied to the dome of the first Planetarium of Jena. As this was the first geodesic dome structure ever built, Bauersfeld has already been rightly praised for his idea. What the findings of this study highlight is that he did not simply invent the geodesic dome, but he aimed at optimizing it as much as possible right away, and he did very good. I thank you for your attention. My contact details are on the slide. Should you have any questions, please feel free to ask it now or later.